Hello, Dr. J again, and I'm going to continue my series of videos on the Laplace transform. We saw earlier that we had a direct application of the definition going from the time domain, description, or waveform f of t to the Laplace domain. We can go the other way, called the inverse Laplace transform, by performing this integral transformation, or what they call is the complex inversion integral, where we go from the Laplace domain to the time domain. Fortunately, because of the uniqueness property of the Laplace transform, we don't have to perform this integration but use the Laplace transform or inverse Laplace transform tables. Now we can use the inverse Laplace transform tables or Laplace transform tables going back and forth between the time domain and the Laplace domain, or the Laplace domain to the time domain, because of the uniqueness property. However, I won't go over that because it's beyond the uniqueness property, because it's beyond the scope of this video. So I'm going to summarize what I did in the previous videos, describing the Laplace transform of a unit step, Laplace transform of an exponential function, and Laplace transform of an impulse function. Okay, so here we have our Laplace transform or inverse Laplace transform, where we can go from the time domain to the Laplace domain, and because of uniqueness property, we can go from f of s to f of t. First, we have our unit step, and we saw that the Laplace transform of a unit step is 1 over s. For an exponential, we have e to the minus alpha t u of t. And for this Laplace function, we have the Laplace transform of s plus alpha. Note, when alpha is equal to 0, this reduces to a special case of a unit step of 1 over s. Now you have this unit step just to show the visibility of causality, because the uniqueness property says that when you go from the f of s to f of t, it always causes a causal function. And that's what this u of t is, to impose causality to this exponential function. Then finally, we have our unit impulse, or our direct delta function. We have a delta of t, and its corresponding Laplace transform is simply a constant. Notice in this description, we have delta t is equal to 1. Now, if you're given this f of s for each of these three functions, then whenever you see a 1 of s, then we can think of the corresponding time domain description is the step function, and 1 over s plus alpha is the exponential function, and a constant of 1 is just simply the delta function. Notice in the last example here, the unit impulse, the delta function, delta t, is very thin in the time domain, but it's very wide in the frequency domain. This is useful such as in Bluetooth applications or military applications, where it's called spread spectrum techniques, where you spread the spectrum in the frequency domain. So sometimes you'll hear me interchange the term frequency domain and Laplace domain, and that's what I'm referring to when it comes to applications in communications. So far I talked about only 3 functions, but we know that there's more functions, like the sine function, the cosine function, a damped sinusoidal function, ramp, and a damped ramp. But in order to calculate the Laplace transform, rather doing the brute force definition, let's go over some of the properties that I'll be talking in the next couple of videos. Some of the basic Laplace transform properties include the linearity. This will be used to generate the Laplace transform of a sine function. We also have the integration property, which will show you that it's 1 over s. And notice the Laplace transform of step is 1 over s. But the Laplace transform of unit step is a mathematical function, whereas this integration property is a mathematical operation. So that's the difference. And then for 0 initial conditions, we have the differentiation property can be reduced to an s in the Laplace domain. And then finally, we have the translation property to describe damped functions like the damped sinusoid and a damped ramp. So these are some of the properties I'll be discussing, with some examples of how to apply these properties as well. Signing off, this is Dr. J.